Welcome back to Chemistry Chapters, and today we are looking at an incredible visual guide that explores the fundamental building block of our entire universe, the atom. If you have ever wondered how the microscopic world connects to the massive world around us, this infographic perfectly maps it out. Let's break down the central atomic structure and the 6 amazing ways atoms govern our reality into a clear, continuous guide for your studies. The core. Structure of the atom right in the center of the graphic, we see a glowing, highly detailed 3D model of an atom. You can think of it as a miniature, high-speed solar system. At the very center is the densely packed nucleus, which contains protons, the red spheres carrying a positive charge, marked with a plus, and neutrons, the gray spheres with a neutral charge, marked with a 0. Zooming around this heavy core on bright blue orbital paths are the electrons, the blue spheres carrying a negative charge. The constant electrostatic attraction between the positive protons and the negative electrons is exactly what holds the entire structure together. The universal building blocks branching out from the center, the infographic highlights 6 major areas where atomic structure dictates how our world works. Starting in the top left, the Everything is Made of Atoms panel reminds us that from the water we drink and the plants we grow, to the stars in the night sky, absolutely all matter is constructed from these tiny units. Moving down to why elements have different properties, we see a snapshot of the periodic table. The reason an element like carbon acts completely differently from silver comes entirely down to the specific number of protons, neutrons, and electrons inside their respective atoms. On the bottom right, the Formation of Molecules panel shows that when these individual atoms chemically bond, they build the essential structures of life. From simple water, H2O, and carbon dioxide, CO2, to the complex, twisted double helix of our DNA, energy and reactions atoms are also the ultimate engines of energy and change. In the top right chemical reactions panel, we see what happens when different atoms collide. They break old connections and transfer or share their outer electrons to form entirely new substances. If we look at the electricity panel in the middle right, we can see those negatively charged electrons actively flowing through a copper wire to power a glowing light bulb. That directed stream of moving electrons is exactly what we call an electrical current. Lastly, the nuclear energy panel on the bottom left demonstrates that the dense nucleus itself holds a massive amount of raw power. When that core is split apart, fission, or fused together, fusion, it releases the tremendous bursts of energy used to generate nuclear power. By understanding the basic anatomy of an atom, we can unlock the secrets of everything from electrical engineering to our own biology. What is an atom? What exactly is an atom? Let's break down this infographic into a clear, continuous guide for your studies. The definition and examples, starting on the left side. The graphic gives us a perfect definition. An atom is the absolute smallest unit of an element that still retains all the chemical properties of that specific element. To visualize this, look at the examples panel on the right. If you were to take a solid brick of gold and continuously cut it in half until you reached a single microscopic gold atom, that tiny unit still behaves exactly like gold. Similarly, a single hydrogen atom still behaves completely like hydrogen. The anatomy of the atom right in the center, we see a glowing 3D model showing how these atoms are built. The atom consists of a dense central core called the nucleus, which is packed with protons, the red spheres carrying a positive plus charge, and neutrons, the gray spheres carrying a neutral 0 charge. Zooming around this heavy core on bright blue orbital rings are the electrons, the blue spheres carrying a negative A charge. Dividing the atom finally, the bottom panel asks a crucial question. What happens if an atom is divided? If you were to break an atom apart into its individual subatomic particles, it completely loses its identity. As the red X indicates, once it is dismantled into just a loose proton, neutron, and electron, the atom loses the chemical properties of its element. It is the specific intact combination of these 3 particles working together that gives every element in the universe its unique characteristics. As we can see in the glowing information panel on the left, an atom is defined as the absolute smallest particle of an element that can exist independently while still retaining all the chemical properties of that specific element. Looking at the right side of the infographic, this definition is broken down into 3 core pillars. First, it is the smallest unit of matter that we can physically isolate while keeping its elemental identity. Second, it exists independently, meaning a single atom is a complete standalone functional unit in nature. Finally, it retains chemical properties, meaning a single microscopic atom of a substance, like gold, oxygen, or carbon, will always react and behave chemically exactly like a massive chunk of that same substance. The sequence at the very bottom perfectly summarizes this entire concept for your studies. When you take an element and break it all the way down to a single atom, its unique chemical properties are perfectly preserved, tied together by the beautifully detailed 3D model of the atom in the center. This infographic reminds us that this tiny, independent unit is the ultimate building block of our chemical universe. Size of an atom. It is one thing to know that everything in the universe is made of atoms, but it is another entirely to understand just how incredibly tiny they actually are. Let's break down this infographic to put the true size of an atom into real-world perspective for your studies. The true measurement, right in the center, we see our familiar glowing 3D model of an atom, complete with its nucleus and orbiting electrons. Above it, we get our first true measurement. The approximate diameter of a single atom is just 0.1 nanometers, which is mathematically written as $1 times 10 d or $10 meters. To put that number into perspective, you would have to take a single meter stick and divide it into 10 billion equal pieces to find the width of just one atom. The human hair comparison, if numbers that small are hard to visualize, look at the panel on the left. It shows a highly magnified strand of human hair, something we consider very thin and delicate in our everyday lives. However, at the microscopic level, a single strand of human hair is actually a massive structure. It is approximately 80,000 atoms wide. Dust particles and molecules. Moving to the bottom section, we see a microscope looking at a simple speck of dust. The graphic shows a clear progression of scale from right to left. A single dust particle is gigantic compared to molecules, holding literally millions of atoms inside. If we look at the water molecule panel on the right, it reminds us that molecules are built by connecting these incredibly tiny atoms together. A single water molecule, H2O, is made of exactly 3 atoms, 1 oxygen and 2 hydrogens. This perfectly illustrates that while molecules are the tiny building blocks of the water we drink, the atom remains the absolute smallest fundamental unit. By comparing atoms to everyday objects like hair and dust, we can truly appreciate the invisible scale of chemistry. The core. What is the nucleus? Starting on the left side, the 1. Nucleus panel gives us the foundational definition. The nucleus is located at the absolute center of the atom. If we look at the magnified 3D model in the middle, we can see exactly what is inside this core. It is a tightly bound cluster of protons, the red spheres carrying a positive pluses charge, and neutrons, the gray spheres carrying a neutral 0 charge. The mass comparison, moving over to the top right, we encounter a mind-blowing fact about how an atom's weight is distributed. While the zooming electrons, the blue spheres orbiting the outside, take up almost all of the physical space of the atom, they are practically weightless. Because the heavy protons and neutrons are bundled together in the center, more than 99.9% of the entire atom's mass is concentrated directly inside the nucleus. Extreme density. Finally, the bottom right panel focuses on density. It can be hard to visualize how tightly packed this core really is. Because the nucleus is hoarding 99.9% of the atom's mass, but occupying a microscopically small volume compared to the rest of the electron cloud, it is incredibly dense. The heavy metal sphere in the graphic is a great reminder of this property. It is tiny in size, but packs a massive amount of weight. By understanding the nucleus, we realize that the vast majority of an atom is actually just empty space, with almost all of its physical reality anchored by this tiny, ultra-dense core. The electron cloud starting on the left side. The information panel defines the electron cloud. Instead of sitting completely still, negatively charged electrons are constantly moving around the central nucleus at lightning speeds. They do not just fly around randomly. They occupy very specific energy levels, which chemists refer to as shells and orbitals. The massive, glowing blue sphere in the center perfectly visualizes how these fast-moving electrons create a continuous, 3D spherical cloud around the core. Mass versus volume moving to the right side of the graphic. We see a fascinating contrast that completely defines atomic anatomy. As we learned previously, the tiny, dense nucleus holds most of the mass. However, the blue spherical diagram directly below it demonstrates that the electron cloud is responsible for most of the volume. The electron cloud occupies almost all of the atom's physical space, meaning that despite feeling solid, everyday matter is mostly just empty space. The front line of chemistry. Finally, the bottom text highlights a crucial rule for all of chemistry. Even though these orbiting electrons have very little physical mass compared to the heavy protons and neutrons, they are incredibly important. Because they exist on the absolute outermost edge of the atom's volume, electrons determine almost all of an element's chemical behavior. They are the frontline workers that interact, share, and trade with other atoms to drive every chemical reaction in the universe. Inshallah, in our next video, we will continue our journey and cover the upcoming topics. I will see you then.